Okay, on a ski weekend in Colorado, Bob, whose mass is 75 kilograms, skis down a hill that is inclined at an angle of 15 degrees to the horizontal and has a vertical rise of 25 meters. How much work is done by gravity as Bob goes down the hill? So, this is 15 degrees, correct? It says, let me reread it, okay? On a ski weekend in Colorado, Bob, whose mass is 75 kilograms, skis down a hill that is inclined at an angle of 15 degrees to the horizontal and has a vertical rise of 25 meters. So that would be this, right? 25 meters. Correct? How much work is done by gravity? So the equation would be the PE is going to equal the KE, the changes, correct? Up here, he has a particular potential energy. Down here, that potential energy is converted to kinetic energy, correct? So I can keep this very simple because I'm given the mass. This is a constant, and then the distance or the height, we'll say, same. The height equals 25 meters. So it's going to be, you're going to plug in. It's going to be potential energy equals mgh, correct? So it'll be, just do it out for me, what is 75 times 10, that's 750, then times 25, what do we get? Okay. We got it right here. What's that say? 18750. Is that correct? So it'll be change in potential energy will be 1875.50. Correct? And what are the unit labels for that? No unit labels, no credit. Misa, what are the unit labels? You don't know? You're looking for help? Want a lifeline? Get ask somebody. What are the unit labels? I can't hear a word you're saying. Joules, very good. Joules. Okay? Joules. Understood? Yes? Okay. Let's right away do number 2. I'm going to erase this. A pile driver. A pile driver, let me just explain a little bit what a pile driver is. We should show a film on a pile driver. I live near the ocean, and they're always using pile drivers. You hear them all day, all night. In the summer, you don't hear them in the winter. A pile driver is simply exactly what it says. Let's say I have a giant telephone pole, or not a telephone pole, but let's say a giant telephone pole. But I don't want to use it as a telephone pole. It's just a giant, maybe a half a meter in diameter, maybe a meter in diameter. And I'm going to drive it into the sand, and I'm going to put a series of them in and use them as a foundation to put a house up. So I need to drive this post into the ground. So you hook up this apparatus right? You hook up this apparatus. Right? You hook up this apparatus, and here's the top of the post. And then you take this giant weight, and you drop it, and then you raise it, and you just literally hammer that post into the sand. And what it does is you put it quite a ways down. And what it does is it creates a solid foundation to build a house. You put enough of them in, it's okay. Clear? So the pile driver is literally a hammer that you're hammering this post into the ground. And you hear it literally all day in the summer. They're always building at the shore, especially after a storm when houses are wrecked. You hear it all day. Okay, a pile driver is a device used to drive stakes into the ground. While building a fence, Adam drops a pile driver with a mass of 3,000 kilograms. So this weight, in his case, is 3,000 kilograms. If you're putting in a fence, it must be an awfully large fence. Otherwise, if you're doing a fence, you dig the hole, you put concrete in there, you put the post in, and it sets. But it's okay. He wants to use a pile driver, more power to it. So the hammer part of this pile driver is 3,000 kilograms. And he's dropping it through a vertical distance of 8 meters. 8 meters. The pile driver is opposed by a resisting force of 5 times 10 to the 6th newtons. So the resisting force equals 5 times 10 to the 6th newtons. Okay? So when you're dropping it on this post, it really doesn't want to go in. It's resisting. It's resisting with that kind of force. Clear? Yes? All right. How far is the stake driven into the ground on the first stroke? How would you set this up? How would you do this? How would you set this up? How would you set it up? Think Newton's third law. Think Newton's third law. Well, if I drop this down, how much potential energy do I have? What is the change in potential energy when I drop that down? Remember, delta, this is number 2 now. This is A2. If I drop that down, my change in potential energy will equal 3,000 times 8 times 10. Correct? This is M, this is G, and this is H. Correct? Give me a value for that. What is 3,000 times 80? What is it? 3,000 times 80. What does that say? 2, 4, and 4 zeros? So 2, 4, 1, 2, 3, 4 joules. Okay, 240,000 joules. Okay? Now, that post is resisting with 5 million newtons. 5 times 10 to the 6th, correct? But now remember, it's got to be equal to one another. So if this is 24 and 4 zeros joules, what's that going to equal? What's the work on the post side of it? What's the work on the post side of it? Well, is it going to be force times distance? Isn't it? And isn't the resisting force 5 times 10 to the 6 newtons? That's how much it's resisting, correct? So now I've got to calculate the distance. So I write 240,000 joules equals 5 times 10 to the 6th D. And I want to calculate D. So do that on your calculator, see if you can do that. It's going to obviously be less than a meter because I've got to divide both sides by this. This is 2.4 times 10 to the 4th. So what is 240,000 divided by 5 million? What is 2.4 times 10 to the 5th divided by 5 times 10 to the 6th? Do you remember how to put that scientific notation into your calculator? Shall I help you? So you're going to put 2.4 second function, find EE, and then put 5, divided by 5 second function, EE, 6 equals. What do we got? It's about 0.5-ish. Yeah, 0.048. Not 0.5, 0.5-ish, 0.05-ish. So 0, so it's going to be D equals 0.048 meters. Correct? And that should make sense if you're thinking about this. So 2.4 times 10 to the 5th divided by 5 times 10 to the 6th. 5 times 10 to the 5th divided by 10 to the 6th is 10 to the negative 1, right? And then 2.4 divided by 5 is about 0.5. So that's 5 times 10 to the negative 1, and then you have another negative 1, so that should make sense. Your estimation should be around 0.05, and that would be correct. We could round this to 0.05, but 2 significant figures is fine. 0.048 meters. So you can see that's not very far, is it? It's like 5 centimeters every time it hits it. So it takes quite a while. These pile drivers work forever. Have you ever heard of pile driver? You may have not realized what it was. Maybe I'll show you a look on, who has a computer? A phone, it's fine. Look up pile driver. Go to YouTube and look up pile driver. It's a great machine. Very simple, but a very important use. Okay? Okay, shall we do one more and then we'll stop the tape? Change. So number 3, we'll do A-3 now. That was 2. 3 is, well, that's a long one. It says, at an amusement park, a ride called the Cyclone is a giant roller coaster that ascends a 34.1 meter hill. So the height is going to be 34.1 meters. Anybody have a pile driver yet on their phone? Did you get it? All right, hold that. We'll stop the tape, and we'll look at that. Okay. All right. So an amusement park and a ride called Cyclone is a giant roller coaster that ascends a 34.1 meter hill and then drops 21.9 meters before ascending to the next hill. Okay? the train of cars has a mass, so it's going to have the second height, is height 1, height 2, is going to be, this is the height of the hill, and then it's going to have a change of height of 21.9 meters. Okay? The train of cars has a mass of 4727 kilograms. Those are the cars. How much work is required to get an empty train of cars from the ground to the top of the first hill? So they don't give you a lot of information here, but here's the ground, here's the first hill, and then it drops and goes to another hill. So this hill here is 34.1 meters. And then this drop here is 21.9 meters. Does that make sense? Does that make sense? Shall I read it again? At an amusement park, a ride called the Cyclone is a giant roller coaster that ascends a 34.1 meter hill and then drops 21.9 meters before ascending to the next hill. Okay? Here's the mass. They want to know, A, how much work is required to get an empty train of cars from the ground to the top of the first hill. Anybody? Can you do it? Did you do it already? What would you do? Okay, MGH, guys. So it's going to be this height, right? Times this times 10. So what is MGH? So the change in potential energy equals MGH. Okay, tell me. Do it on your calculators. What is 34.1 times 10 times 4,727? Okay, may I go on that? Isis has it, and she has the change in potential energy as 1611907. Okay, and that's joules. All right, that's what she has. And that's going to be A. Thank you. Does everybody have that? Do we have a verification on that? You get that, Ethan? Okay. And then it says, what power must be generated to bring the train to the top of the first hill in 30 seconds? Power equals work over time, right? So this is the work. So what's that? That value. So B would be this value here divided by 30. Shall we write that down? So the power equals 161,1907 divided by 30. 30 seconds, that's an S. S for seconds. So what's that quotient equal to? Anybody got it? 53,700. Can we round it to that? Okay, we'll round it to 53,700. And what are the unit labels? What are the unit labels? What are the unit labels? What are they? What? Not what. What? You get it? I know, science joke. All right? So ask yourself, what are the unit labels? And it may be watts. I know. Issa, you're disgusted. I know. Darcy thinks he's funny. Okay, you get it? Now C, was that C? It says, how much potential energy is converted to kinetic energy from the top of the first hill to the bottom of the 21.9 meter drop? It's really this, isn't it? It's this. So it's going to be the mass. Do this. So the mass is 47.27. G is 10 times 10 times 21.9. What do we got? What is MGH? Delta PE, delta potential energy, change in potential energy. He says on the ball, we got 103, 5, 213. 103, 5, 203. And that's joules. Okay? Questions? Yes, Issa. Wait a second, hold it. Time out. What did you say? 213, not 203. Okay, we can do that. Issa, did I make a mistake? Is that correct? It's 213. Okay, so we have a correction. I love when students correct me. I love it. Love it. You know, over the years, I've seen teachers get very upset when students correct them. Have you seen that? I love it, because you know why? It means they're paying attention. Really good. Excellent. Well done. Thank you. Okay, now, are we done? So we'll stop the tape. We'll look at a little pile driving. Yeah? All right, very exciting. Are you excited, Misa? On the edge of your seat, I know.